Hi, today's lesson, section P5 from our textbook about factoring. And really factoring is just the way of breaking down an algebraic expression into pieces which multiply together to make that expression. So factoring is our goal today. We're going to look at several different things. First is using the greatest common factor, and you'll remember this very quickly once we get started. When we factor out the greatest common factor, what we're doing indeed is using the distributive property in reverse. If you think about that for a moment, remember the distributive property is the one that says A times the quantity B plus C equals AB plus AC. Well, what we want to look for when we're factoring is what is it that these two things can both give up so that we can make it look like this. What can we pull out of these two terms so that we can bring it out to the front and leave everything else behind? And as you look at this problem, our first example, we have 10x cubed minus 4x squared. And you think to yourself, okay, the biggest thing that divides into both of those terms evenly, well, they're even, both even numbers, so 2 goes in there for sure. And the largest number of x's that we can take would be 2, because this one has 2x powers to give up. This one could give up 3, but it definitely has 2. So the greatest common factor is 2x squared for this one. So if we're going to complete this factoring, we would think to ourselves, okay, 2x squared is what they can both give up. And then the next step is to say, okay, if I divide a 2x squared out of here, what am I left with? Well, 2 goes into 10 5 times. X squared goes into x cubed x times. Or think backwards, because remember we're working backwards. If I multiplied 5x times 2x squared, I'd get right back there to that 10x to the third. We have a second term we've got to deal with here, and I'm going to just bring the net minus sign down. 2x squared goes into 4x squared twice. So here's that factored expression, reverse of the distributive property. So as you take a look at this, I have it under the same thing, greatest common factor, but it looks a lot different. And some of us might look at this and say, well, shoot, we've got to distribute here. But the fact is, we really don't. The biggest thing that each of these terms can give up, folks, it's that x minus 7. We can draw that right out into the front and think about what's left behind if we divide out x minus 7. 2x is left from that first term. And of course, 3, positive 3, or plus 3 from the second term. Reverse of the distributive property. Our next type of factoring by grouping, this one may not seem as familiar to you. However, we're going to apply the same concept that we just did, drawing out a greatest common factor, but we're going to do it twice. We're going to take this thing and set it up into two groups and look for the greatest common factor here. Okay? As you think about that, the biggest thing that each of these, well, the constant here is 1 and here's 5, so we can't divide by a constant, but an x squared could definitely come out of there. If I took an x squared out, what I'd be left with in that first parenthesis is x, because x squared goes into x cubed x times, plus 5. All right, so we've factored that first group. As you look at the second group, that's negative 2x minus 10. We could take a negative 2 out of both of those terms. And that would leave us with an x here, negative 2x divided by negative 2x. Negative 10 divided by negative 2 plus 5. And look at that, folks. We've got two terms here that both have an x plus 5 that they can give up. This problem, exactly like this one now. X plus 5 can come out to the front, and what would be left over is an x squared from up here and a minus 2 from here. So we factored that thing by grouping. Not every polynomial that has a cube in it is going to work this way. However, it is something to think about if you are stymied. If you can't find another way to factor, this might be something to look for. Our next factoring type of problem, we're going to remind you of what you did in your algebra classes. We're going to factor trinomials, three-term polynomials, using the box method. This will work for any factorable quadratic that looks like this. Ax squared, and I'm going to make my a's lowercase, plus bxy plus cy squared. Okay? Now, as you think about this, what we're saying is numbers up here with a squared power of our variable, here a middle term that has that variable at 1 power, and here a constant and another squared term possibly. They won't all have all of these components, but this one fits. A would be 1. Y, according to this, must be 1 because B is minus 5. C is minus 14, and Y again 1 in this one. So it doesn't have it. It doesn't look exactly the same. However, it fits that same pattern. Factoring using the box method. I hope that you'll remember this. We start out here with the box, and we think to ourselves, okay, the parts that we know that we're going to use, x squared here, minus 14 here. And then we move to the x. Okay. If you'll recall, what goes on top in the x is this minus 14 times coefficient 1, So negative 14 times 1, we got to have things that multiply to give us minus 14, but they have to add up to give us minus 5. If they're going to multiply to be negative, and that means that you have one term is going to be positive, one negative. That's the only way you can multiply and get a negative number. And this tells us that since the sum is going to be negative, the larger of our factors has to be the negative number. So we're thinking of things that go into 14, and the thing that pops to mind is 7 and 2. So you think to yourself, can I combine a 7 and a 2 in order to get 5? Sure. If I make the negative or the 7 negative, and I make the 2 positive, that works out. Negative 7 times 2, negative 14, negative 7 plus 2, negative 5. These values are the ones that we put inside the missing squares. So we're going to minus 7x here, and we're going to positive 2x here. One thing that I want you to remember, you're not finished when you do the x. You have to come back to the box, and the process is you pull out the greatest common factor in a column or a row, and I'm going to look at this column. This has an x squared, this has a minus 7x. The biggest thing that those can both give up is an x. Now you're good to go, because you think, okay, this x squared comes from multiplying column times row, so this also has to be an x. And you think to yourself, okay, this 2x is the result of multiplying a column times a row, and if x is the row, then the column must be 2. X plus 2 up here. In a similar manner, this has to be negative 7 because it multiplied x with some number to get negative 7x. So our factors here are x minus 7 and x plus 2. Many of you will remember, if the leading coefficient is a 1, you can take the shortcut and say, once I get here, I know what my factors have to be. The danger is that leading coefficient is not always 1. In fact, here's one where it's not. So let's try this one with the box method. And if you want to challenge yourself, please do. Pause the video, work this one out, see if we come up with the same thing. We put into it the 2 parts that we know have to be 3x squared and a 4y squared. And we think to ourselves, okay, now we're ready for the box. Or the x, sorry. We got to have a 4 times 3, that's 12. things that multiply to make positive 12, but things that add to make negative 13. Okay, I think I'm seeing those. If they're adding to be negative but we're multiplying to be positive, they both have to have negative signs with them. And 12 and 1, I think, are the factors that we want to grab. So in this box, negative 12 xy, and this one, negative 1 xy. And now we're at that point where we want to draw out the greatest common factor. And the biggest thing that both of these two can give up is an x. Now we start working backward. If this is x, then this must be 3x. That's the only way we can multiply to get 3x squared. 3x multiplied something to make this, and that something has to be negative 4y. Do you see why the y has to be in there? 3x, negative 4y, negative 12xy. Down here, if x went into this multiplication, then a negative y must have been the thing that multiplied in order for us to get negative 1xy. So now we're looking at our two factors as being x minus 4y and 3x minus y. I love factoring. It's like a puzzle. Unfortunately, you can't always use it because not all quadratics are factorable. Our next type of factoring, we're going to look at some of the more common factoring patterns, and there are several. The first that I'd like to discuss is the difference of squares, and I'm hoping that by the time we're finished with this little demonstration, you will have remembered that very well. What I'd like us to do is just look at the pattern, and so I'm going to say, if you see a binomial where you're looking at a perfect square in the first term minus a perfect square in the second, this pattern will fit. And the way that factoring will work out is always the same. You'll get the square root of the first term plus the square root of the second multiplied by the square root of the first term minus the square root of the second. A plus b, a minus b. Okay. Square root of the first term, square root of the second term, once with a plus, once with a minus. Now, of course, this one's probably going to follow that pattern since it's in the spot in the video. So I want you to think about this for just one moment. We need the square root of the first term. So the square root of 81 is 9. The square root of x squared is x. So we're looking at 9x. We're going to have the square root of the second term, and the square root of 49 is 7. The way I think about this, we're going to have it once with a plus and once with a minus. Now, if you're not believing me, you should go back and try the X box here. In fact, maybe this is a place where I'm going to just divert over here and show you that this works. A squared plus b squared is what we're looking for. And we have a squared in this box minus b squared here. If you think about what has to happen, when you multiply negative 1, when you add, you have to get 0 since there's no middle term. And the only way that that can happen is if you have a negative 1 and a 1. So we'd come back in here and we would say that this is negative 1ab and this is positive 1ab. And as you draw out the greatest common factor, an a would come up to the top and also on the side. This must be plus b if it's going to come out to be ab plus b. This has got to be a minus b if we want to get negative ab out of it. So our two factors, a plus b, a minus b, that difference of squares pattern will always work. Okay. The second set of patterns that I'd like you to get familiar with are called perfect square trinomials. And this pattern has a squared first term, a squared last term, and the center term, the middle term, is twice times the square root of a times the square root of b. Now that sounds a little bit weird, but that's what we're going to be looking for. The factoring pattern here is this: a plus b times a plus b, or a plus b quantity squared. Again, as you think about this, you'll see that it has to be true. If you run this distribution through your head real quick, like a times a squared, outsides a and b, insides a and b, that's 2ab's. The lasts are b and b squared. Has to work. Perfect square trinomial, it's called. And what you're looking for, if this factoring pattern is going to work, is that middle term is going to be twice the square root of the first term times the second term. That'll make more sense when you see numbers with it. If that middle term is a subtraction, then what you're going to end up with is an a minus b squared, or an a minus b times an a minus b quantity squared. Okay. Factoring patterns are there to help us work quickly. So again, these examples wouldn't be here if they didn't fit. So let's just check out what has to happen. The leading coefficient here is 1, and the square root of 1 is 1. The constant is 49, and its square root is 7. So if we think 7 times 1 times 2, that's 14. That means we fit this pattern. We've got positive signs in here. So without doing any box method, if you trust me, we should be able to say that this is x plus 7 times x plus 7. It works nicely if there's no leading coefficient. It's easy to see what's got to happen there. The next one is a little bit more difficult to see. However, again, if you think about, we wouldn't put it here if it didn't fit the pattern. The square root of that first term is 4x. The square root of the last term is 7. 4x and 7. So that would be 28x, and 28 twice is 56. So we fit the pattern. It was just harder to see here. So we should be able to split this one out. It's the square root of the first thing, 4x, and since this is a negative middle term, minus 7, 4x minus 7. That perfect square trinomial pattern, this one is always a little bit more difficult for me to see, but works every time, which means we love it. Let's go to the next factoring patterns that we want to talk about, the sum or difference of two cubes. For a sum of cubes, the factoring pattern goes this way. One of the factors will be a plus b, or the second factor will be a squared minus ab plus b squared. If it's a difference of cubes, signs change. So a minus b is the factor that you can bring out. The quadratic that will be left, a squared plus ab plus b squared. Okay, so a little bit of difference in the signs there. Let's see if we can apply that here. The straight plug and chug case, as my old friend Mr. Metzlar would say. X cubed plus 1. So a must be x, b is 1 in this one. Okay? As you work out the pattern, you think to yourself, what you're going to get as a factor, a first factor, is x plus 1. The second part of this has got to be the square of this guy, so x squared, minus, and it's x times 1, so minus x, and then plus 1 squared. And we factored that guy by using that factoring pattern. Not every cubic, of course, is going to look exactly like this one. However, if we get a cubic where it's just two terms, this is a good strategy to check. As you think about this, it wouldn't be here if this didn't work. Okay, that must mean that we can take a cube root of this, because we need the cube root of that whole term, and the cube root of 125 is 5. So a in this one, I'm going to just write this out to the side. A is going to be 5x. B in this one is going to be the cube root of 8, and the cube root of 8 is 2. Let's see if we can't follow the pattern now. We've got a difference, so we're looking at this one. This is going to factor as a minus b, so 5x minus 2 multiplied by it's a squared. If we square 5x, we get 5 squared, which is 25, and x squared. Then it's plus a times b. A is 5x, b is 2, so we're talking plus 10x. And then the last step says plus b squared. If b is 2, that's plus 4. And we factored that difference of cubes using that pattern. It always helps, especially in the ones that are more complicated. Give yourself a guide. Set it up as a equals so that you know what you're working with. That'll make it a little bit easier for you. This says factor completely, and this is our last example problem for this lesson. Folks, when you see this factor completely, you might think this could be a little bit more involved than some of the others we've looked at. I do see that we've got an even exponent here, a difference, and it's a binomial. Is this a perfect square? Yeah, I think so, because 81, the square root of that is 9, and the square root of x to the 4th is x squared. Is this a perfect square? Yep. We're going to apply that difference of squares pattern. And if you recall that, difference of squares says square root of the first plus square root of the second, square root of the first minus square root of the second. So I better figure the square root of the first. 9x squared. The square root of the second thing is 4. We're going to use those two things, once with a plus and once with a minus. And I'm looking at that thinking, yeah, that looks pretty good. I did that thing. And then I think, okay, they said factor completely. Maybe I should look a little bit further. This is a sum of squares. We don't have a pattern for that. So we kind of have to leave that alone. But y'all, this is a difference of squares again. This is a perfect square. This is a perfect square. So we can factor that last parenthesis down. I'm going to rewrite the first one, 9x squared plus 4, because that's just going to be part of my final solution here. But then I'm going to think square root of the first, 3x, square root of the second, 2. I use it once with a plus and once with a minus. And that, dear friends, is factor completely. So we hope that you'll take a look next at the U-Try for this lesson and practice those factoring skills. In class tomorrow, we'll have many opportunities to practice. Have a good night.